Hello, everyone. I'm Joshua. Thank you for allowing me to present today. I'm going to be presenting about the multi-beam terminal design that I have made during my master's thesis, and that is going to be continued during a PhD project in the next coming round. And this project was done at the Aerospace Engineering Spaceflight Department. And some work has also been in collaboration with the Applied Physics faculty. So a little bit of background first. Basically, as we have heard many times before, the amount of data that's being consumed in the world is exponentially increasing still. And this also has some interesting ramifications for space. So for one, mega constellations are becoming more and more prevalent. Just look at Starlink, which is also expected to take some of the internet data throughput through it. So it needs to be able to handle quite large amounts of data streams through space. And on top of that, we have to also design terminals in order to be flat packed, easy to integrate, and easy to manufacture with existing technologies. There's also in space itself is becoming also more and more interesting. From an Earth observation perspective, we look at the Copernicus missions, for example, with an almost live view of a lot of very high quality, high resolution data from space of the Earth is already changing the way we sort of interact and live on the planet. Currently, a lot of this data is put through data relay systems, such as ERDS, European Data Relay System. And as you can see, it actually currently has quite a wide suite of different methods by which it communicates, so radio, but also laser, with single laser beam terminals. And this is one of those satellites, and if you can see it's just a lot of these satellites also have quite prominent antenna systems on them. And if you were to consider the launch costs, such heavy and power intensive subsystems also cost quite a lot. So there's opportunity there. There are already some laser communication terminals on the ERDS satellites. And as you can see, there's already the form factor is quite substantially smaller, and their performance is also quite good. I actually pulled out an old textbook of mine to determine what the rough estimation would be of a radio communication system, and then compare it to the current comparable laser communication terminals. And as you can see, there's orders of magnitudes difference, and in space that means an enormous amount of cost saving. Kerry Cahoy from MIT actually made a really nice overview of what sort of looks for the microsatellite laser communication terminals. As you can see, the amount of power being consumed is quite low, while there's still really respectable. Particularly Node is quite interesting. So the miniaturization of these terminals has progressed quite substantially over the last couple of years, and we're now capable of fitting in a laser communication terminal onto about 1.5 units for a cube satellite. And they're actually quite simple in terms of their operation. So as you can see, there's a simple transmitter with a fast steering mirror, there's a telescope, and there's beacon cameras for course pointing. And what's interesting is that these systems don't even use closed loop operations in order to be able to communicate with these data rates. What's also kind of interesting is that they use separated telescope and beacon cameras, whereas also the transmitter and the beacon themselves are also separate systems. And so there's still quite some improvements that can be made in terms of the part counts on these kinds of systems. So the overall goal of the project was to actually design a multi-beam laser communication terminal, which could also take some of the traffic that is still going through radio communication, and be able to put that into a format that is also swap friendly, almost as swap friendly as the CubeSat miniature laser communication terminals we just saw. So there was a couple of design goals. I wanted the close feedback loop for for more accuracy and resilience. There's also multi-beam steering mechanisms, which we'll talk about in a bit. Shared components between beams in order to reduce the part counts. Have no required beacon, also to reduce power consumption. And also be able to do multiple duplex communications. And also design all of this with commercial off-the-shelf components in order to ensure that both economical as well as reliable. And it would not necessarily require huge advancements in technology to achieve multi-beam communication. So I will first talk a bit about how I designed the system. I think it's quite interesting to see what I learned there. And then also I'll jump into what the system performance should be. So if we consider two options here, there's two main ways I found that you could steer multiple beams at once. Is either you steer the incoming beams or you steer the outgoing beams. And what I found is that there's actually quite a significant difference. So on the left, you can see that it's actually steering incoming beams. And on the right, you can see that it's steering outgoing beams. So you can see an arrow which direction is incoming. And what's interesting is because you know where the transceivers are, and you know where the origins are of the transmitted beams or the outgoing beams, then you can actually track half the number of beams required for duplex communications. And so it actually the orientation or the exact architecture you choose for beam steering is quite important. Then it's actually also already mentioned previously in previous presentations today, is that you can actually combine and make the incoming and outgoing beam travel along the same path. The result is that there are you only have to track one set of beams for both incoming and outgoing beams. And as a result, you can actually steer twice the amount of beams and therefore have twice the amount of utility out of such a system. And at the cost, of course, of adding one more steering mechanism for the system. So even though it becomes more heavier and the part count increases, the number of beams or the utility of it is improved by a factor 2. And there's also a hidden benefit to adding a second steering stage. It allows you to actually choose two different steering technologies to be used for separating these beams out and steering them. I illustrated that here. What I found is that you can actually combine the speed and reliability of the MMA to filter out higher frequency offsets and vibrations and jitter, as well as utilize its accuracy, and combine that with the high resolution steering of SLMs, for example. And what is actually particularly what I found was that the resolution of the steering mechanism system is actually really important for the performance. So if you have, for example, in this case, on the left, let's see if I have a pointer. On the left, you actually can see like quite a coarse steering mechanism with 3 mirrors mirroring 3 beams onto 3 different targets. So these beams reflect off of these mirrors onto these targets. And when they're far enough spaced, when they're spaced far enough, this is fine. However, when the beams become closer but not yet interfere with such a coarse mirror setup, you can start to have diffraction effects. And this is because these beams all of a sudden are diffracted over a quarter or a half of a pixel along the boundary. And that's actually the benefit of using an SLM, because you can actually make your reflective steering surface much smaller, and you can actually start reaching the limits of where these beams will actually start interfering before we lose, before diffractive effects start becoming a major issue in the communication. So that's actually the reason why there is two steering stages, and why it's so important to actually have this combination between fast and high resolution. What's more is that because we also use the same path principle, or the incoming beam and outgoing beams occupy the same space, it actually allows you to separate them in fiber. and also use fiber optics in order for your high performance fiber optics for your transceivers. And that also increases the utility and compatibility of these systems enormously. So this is actually a schematic of the system that I designed, where you can see the major components here. So you have the SLM on this end, and the micromirror array on this end, and then you have their individual spot trackers as well. And what's also interesting about this setup is that they can actually operate in their own feedback loops semi-autonomously, which also increases reliability, because you also have limited functionality still when one of these systems fail. So this is another view of the overall system. I made also a very sketchy looking 3D render of what it would look like. And the reason why it's actually so spaced out is because the SLM doesn't have very far throw when it comes to steering. But it's actually kind of comparable to a serial box, if that makes sense. So that allows for scalability in these mega constellations. So we also did some modeling in order to gauge the performance. It's actually also, this system has been built and has been tested, but I do not want to get into that because the researchers, it wouldn't be fair to the researchers involved. So I can't share any data of that yet, but the model and modeling simulation still illustrate interesting aspects. So what I did was, with the input beams, I also added jitter, and then I had a custom propagation tool and a basic feedback loop through and a custom designed algorithm, which then also steered the beams to the correct location. And this is one of the runs. I took a couple of frames out in order to speed it up. But as you can see, there's some complicated things happening here. This is the SLM applied phase. And as you can see, it actually tracks these beams really well. But there are a couple of points where errors are introduced. So this is actually the graph that shows the pointing error over time. And there's two large error events. The first one is where the spots move over each other. And so as these spots start interfering, the algorithm and the system cannot tell them apart anymore, and it starts pointing them in wrong directions. However, when they start again being unresolvable, it treats them as one beam until they start becoming resolvable again. So that's why you actually see these two peaks. And then you also have of course, the error peaks when the beams move in and out of frame. So in total, what I found was that this is quite a representative case when beams cross each other, is that about 11% of the time when the beams are crossed, we have about a 5% downtime for unaffiliated spots, but this can be reduced down to 0 by improving the algorithm in order to make sure that it's not affected by these other crossing spots. So yeah, I hope you found that interesting. I'll be open for some questions, and yeah, let me know what you think. Thank you.